So the theme of this week's videos really focus on how do reactions happen. We're going to learn some physical components of reactions happening, see their dependence on temperature. We'll talk about reaction mechanisms based on data. We'll talk about catalysts and how they affect how reactions happen. And then we'll start talking about equilibrium, which really just goes to speak to why directions happen or reactions happen. What's the driving force behind it? And so we'll be working on that this week. And so when we think about a reaction happening in chemistry, it may be as simple as something as two molecules, let's say a hydrogen and an iodine, coming together. And of course, these are not drawn to scale, right? Hydrogen is much smaller than iodine is. But really, as we consider what's happening here is we're making two molecules of HI. But how does this actually happen? Well, we have to consider that since this is a gas phase reaction, and most reactions that we will talk about either are gas phase, liquid phase, or solution phase. We don't really have solid state reactions happening too much, but we see what happens is that these two molecules, the hydrogen and the iodine, need to collide together. And in doing so, once they collide, they have to break the bonds that they already have, and they need to form new ones. And so we're going to explore that here. And so we're really looking at a couple of things. We want to think that first off, for a reaction to happen, let me preface that, for a reaction to occur, we really need two things to happen. We need the molecules to collide at the right angle to each other, in the proper orientation. And if we think about it, molecules are constantly slamming into each other. And your book brings an interesting comparison. If, say, a molecule of hydrogen and iodine hit each other, how about 1 trillion times per second, we'll say. But really, only 1 out of 10 trillion collisions is in the right orientation for it to react. And so the other 9.9 trillion, over a course of 10 seconds, really doesn't react, despite the fact that they're hitting each other. And so the orientation factor is very important. Otherwise, all reactions would happen extremely quickly. But suffice it to say that, we need molecules to hit each other the right way. If they are coming into contact with each other the wrong way, a reaction doesn't happen. And you would think there's 360 degrees, right? We have a sphere around a molecule, and it needs to hit in exactly the right angle to hit. So maybe it's not going to react if it hits this way. If one of them is vertically or horizontal, they don't hit. Or they don't hit properly, there's no reaction that happens. Things need to happen perfectly. They need to align exactly correctly for a reaction to happen. And the second consideration is, even if they hit in the correct orientation, which is something that catalysts will help with, by the way, as we'll preface that later on. Catalysts help molecules find the correct orientation. But the molecules need to have sufficient kinetic energy when they collide. So not only do they have to collide the correct way, as in the correct angles, but they also need to hit each other hard enough. We need to have enough kinetic energy to break the bonds that are being broken so that we can form the new bonds. And so, oh gosh, this is terrible. Let's fix that word. Energy. So they need to be able to hit each other fast enough as well, hard enough to break their bonds. And we know from when we talked about gases originally, at a given temperature, maybe this is our graph of the proportion of molecules. Maybe that's a percentage. And this is the kinetic energy down here. At a given temperature, a certain proportion of molecules will have sufficient kinetic energy to be able to react. But as we know, if we increase the temperature, we'll end up shifting this graph over a little bit. And now we have even more energy. So the blue one is the higher temperature graph. Remember that temperature is related with kinetic energy. So the higher temperature you are, the more molecules have the specific amount of kinetic energy needed for a particular reaction. And so we'll see, for reactions in general, increasing the temperature will increase the rate. As we know, K is temperature dependent. As we increase temperature, we increase K, the rate constant. And just goes to show, or just it happens to be, that every change in about 10 degrees Celsius equals a doubling of the reaction rate. So even just 10 degrees Celsius is enough to double your reaction. And so that's why it's very bad for humans to be in a fever or hypothermia, because reactions are very sensitive to temperature, their rates. And so reactions we may not be wanting to happen in our bodies happen much more quickly when we're in a fever. Or reactions that we very much need to happen more slowly in a hypothermic setting where we're too cold. And so our bodies, as we know, are very sensitive to temperature. Back in, the 1300 or whatever, if you got a fever of 103, you were dead, basically. And that's only, 5 degrees Fahrenheit, which is 2 degrees Celsius. That's not even close to doubling of the rates. But suffice to say, biological systems are very well attuned to specific temperatures. And if you mess with those, you mess with the rates of those reactions. And then things go out of whack and bad things happen. So suffice it to say, rule of thumb, every 10 degrees Celsius you increase. So if you're going from 50 to 60 Celsius, you're doubling your reaction rate. If you go from 50 to 70, you are quadrupling your reaction rate. Right? So it's a change in temperature of 10 degrees Celsius. So increasing it by 10 degrees doubles your reaction rate. And so we're going to see in our next videos how to mathematically deal with this idea of temperature and rate.